right, 4.6 is modeling exponential and logarithmic functions. And this first video is going to show an exponential growth model. So your ratio needs to be more than 0, clearly, to make it grow. So I just have a couple examples that we'll walk through. But the box formula here is what you will use for any population that's experiencing exponential growth. The variables are defined below, as you can see, but they will not be defined on the test, so just make sure you're comfortable with what they represent. So N of t is your population after a certain amount of time. N sub 0, or N naught, is your initial population size, so it's kind of like starting, ending. R is your rate of growth, which may or may not be given in the question. And T is time, and that's going to be specific to the problem. So if the problem says days, hours, months, you just follow that same time. So here's our first example. If you read it, it says a culture starts with 320 bacteria. After just 30 minutes, the count is to 4,580. So clearly it is growing. You can see that starting with 320 going to 4,580. So you know it's going to be an exponential growth situation. Part A says find the formula for the number of bacteria after t hours. So using the given formula, N of t is the final count. So this is my N of t. And N naught, or N sub 0, is the initial amount of bacteria. So plugging in what I know. And the rate of growth is what I don't know. So I'm going to just keep R as R. But I do know that this goes from start to end after 30 minutes. And time is in hours, so please make sure you catch that. So that's going to be 0.5. If you do the algebra to solve for your rate, you'll divide by 320. And then you can put it into logarithmic form, so natural log both sides. And that will bring us to the natural log of that quantity. And that's going to equal 0.5 R. To solve for R, at that point, you would divide by a half, but being it would be a fraction over a fraction, instead of multiplying by half, I would probably just double both sides to get rid of that to solve for R. So when you then go to plug in R, this right here, this expression is R, you're going to replace R in the formula with that, so you can see here that I have the exponential growth model. So 320 was the initial amount, and my rate, I would keep my rate right here as an exact value. You can certainly see what that is as an approximation on your calculator, but keep it as an exact value in your work. Okay, part B says find the whole number of bacteria after 2.5 hours. So now you're just going to take the equation that we built, and you're going to plug in 2.5 hours for time. Okay, so now it's just a matter of typing that into your calculator. And I would be real careful as you type your 4,000, what you're natural logging right here. That's a fraction, so you would need lots of parentheses. So maybe take a second and pause the video and make sure that you get that number. Because while this sounds like easy, like just dump it in your calculator, it's also real easy to not have a parenthesis in the correct spot, or use your fraction button if you prefer. Part C says, after how many minutes will the number of bacteria triple? So if it started at 320, when you triple, 320 times 3 will be 960 bacteria. When you plug in 960 for your N of T and divide by 320, of course, that's where you get the tripling effect right here. And beyond that, it is, again, kind of using your calculator. Of course, to solve for time is my exponent, I'm going to have to natural log both sides. So you end up with the natural log of 3 equals 2 times that natural log quantity there. That, and then times t. As you type this in your calculator, you will divide by this entire quantity. So divide by that to natural log of 4580 over 320. And that will give you time. Keep in mind that when you get that, time is in hours, and we want the time in minutes. So if you take the 0.206 that you get from your calculator, and I rounded generously, times 60 minutes in an hour, you'll get 12.4 minutes. So just pay attention to your units. That could be the tricky part for sure. Okay, second example I'm going to go through a little more quickly because it's not any different. You have some different pieces given. So you have a certain breed of rabbit was introduced onto a small island about 9 years ago. The current rabbit population on the island is estimated to be 4,700 with a relative growth rate of 55% per year. So again, you realize it's growing. Part A says, what is the initial size of the rabbit population? So we know 9 years ago, and we have the 4,700, which is the current population. So if you plug in to your growth model, 4,700 is the current population, and n sub 0 is what it was 9 years ago, and we're not sure what that is. So plugging in the rate of 55%, and the time was 9 years ago. Then from there, to solve for n sub 0, you can divide by the e raised to 0.55 divided by 9. So this would be your n naught. Okay, so if you take that into your calculator, the initial rabbit population is 33. Make sure you round that to a whole number because we're talking about rabbits. Then part B says estimate the population after 11 years. So now we're just plugging 11 in for time, and we know our initial population is 33 rabbits. So again, if you type that into your calculator, you should get 13,995 rabbits. All right, we will switch gears to the exponential decay model. We're going to talk about problems that involve radioactive decay. You can see the formula. Again, it's given. In fact, I'm going to box this in. This is what you're going to be given. Okay, and that is it. So m of t is your mass remaining after a certain amount of time. M sub 0 is your initial mass, very similar to exponential growth. R is your rate of decay. T is also time specific to the problem. The unique thing about radioactive decay is you're going to have a half-life. So H represents your half-life, which will be given in the question, so a certain amount of days or whatever it may be. You will use this equation right here to find your rate. So that's the unique part about a radioactive decay model. So H is your half-life, which was given. Take the natural log and divide that by H, and you will have your rate. So reading example 4, it says polonium-210 has a half-life of 140 days. Okay, so there's your H. You be labeling things as you go. Suppose a sample of this substance has a mass of 100 milligrams. So there's our initial mass, m sub 0. Find a function that models the amount of the sample remaining at time t. So first thing is you need to find your rate. And using the natural log of 2 for half-life divided by the half-life. So I know that my rate is the natural log of 2 divided by 140 days. Because that's my half-life. And I would keep that in exact form as well. Don't dump that into your calculator yet. So now if you plug everything else into the radioactive decay formula, you know that your initial mass is 100 and your rate now is the natural log of 2 divided by 140. So those are kind of your pieces that you fill in. Then when you get to part B, find the mass remaining after 1 year. Notice half-life is in days, so 1 year I convert to days as well. So that's 365 days. So when I plug in 365 days for time, again, then it's just a matter of typing that into your calculator to get 16.14 days. And then in part C, after how long will only 3 milligrams of the sample remain? So now I know I'm starting with 100 milligrams and I'm going to go to 3 milligrams. So that's my ending amount. Natural log of 2 divided by 140 is still my rate. And now I can algebraically solve for time. So you're going to divide by 100. And then you will natural log both sides. So the natural log of that quantity will equal my rate times time, and then divide by this quantity to solve for time. Be careful, you have a lot of fractions here happening, so take a second and pause the video and make sure that you can take that into your calculator. Honestly, the hardest part right there for some people. And you should get 708.4 days. So there you have exponential growth and radioactive decay. Fairly straightforward in terms of using the formulas. I can't stress to you enough to make sure that you can type this all into your calculator. Dropping negatives, incorrectly putting in a fraction, that can really mess up your question. So make sure you also make sure that your answer is logical. If it's not, go back and check your formula and check what you've typed into your calculator.